These notes are about hyperbolas, our last conic section of the unit. Do you remember how we got the hyperbola when we sliced up the cone? That was kind of when we sliced the cone somewhere down the side, so we got the top part of the cone and the bottom part of the cone. And so we ended up with these kind of two branches, and those two branches collectively are known as a hyperbola. Here's the definition of a hyperbola written at the top. If we're given two foci, f1 and f2, a hyperbola is a set of points, P, such that the difference in the distances between any point, one of the foci, and the point to the other foci is constant. So we're subtracting the differences from any point in that hyperbola to each focus, and that difference is always constant. You can kind of relate this to an ellipse when we have the sum of the distances is constant. It's a little bit harder to envision with the hyperbola, but we will take a look at what some of the graphs look like. So in pink, we have the two different forms of an equation for a hyperbola. Notice because we have subtraction here, we have two ways that you might see the equation. X squared over a squared minus y squared over b squared equals 1. And then because it's subtraction, of course, the y squared over b squared coming first is not the same. So what's the difference in these hyperbolas? Let's think about what points make sense here. In the first example, we are going to have x-intercepts, which means our hyperbola is going to look something like this, what the hyperbola might look like. You can kind of imagine slicing a cone. We can kind of see our two branches there. And notice that this hyperbola has x-intercepts. It's never crossing the y-axis. Now, of course, later we are going to shift these hyperbolas, so our center is not always going to be at 0, 0, but for the first few examples, we're going to stick with that. So it has x-intercepts because our x squared term is coming first. I can plug in 0 for y and I can solve for our x-intercepts. But if you imagine plugging in 0 for x, you're going to get that a negative y squared equals 1, which can't happen. So if we have our x squared term coming first, we have this kind of horizontal looking hyperbola. If we have y squared coming first, we have this more vertical hyperbola. And that for the same reason. You can plug in 0 for x right here and solve for y, but if you plug in 0 for y, you're going to get that x squared equals a negative number, which doesn't make sense. So we have to be careful with the orientation of our hyperbola here. Notice we have a squareds and b squareds in the denominators, kind of like we did for the ellipses as well, and they're telling us something about the wideness of the hyperbola. We're going to do some examples later on that we'll see really what a and b are telling us. But still kind of in the more general sense, if we think about, again, how we sliced that cone to get a hyperbola, we can see that off at the ends, the hyperbola is going to kind of take the shape of the cone. What that means is we actually have asymptotes when we graph a hyperbola. I'll probably state this again later, but just since we're here and I can see where the a's and the b's are in the equation, our asymptotes, before we shift anything, are going to be y equals plus or minus b over ax. So there are two asymptotes, b over ax and negative b over ax. And again, when we do some graphing examples, we'll see why that's true. Let c be the distance from the center to the focus. That should kind of ring a bell because I think that's what we called c in the ellipse as well. We had a relationship between a, b, and c for the ellipse, and it's going to look a little bit different for the hyperbola. For the hyperbola, our relationship between a, b, and c is that a squared plus b squared is equal to c squared. C in this case is the longest of the three distances. Let's actually graph these and see how we can see a and b and c in our graph. Our first example, x squared over 9 minus y squared over 25 equals 1. It's not shifted, but from our previous form we can see that a, which I'm going to leave under x, a is going to be 3, and b here is going to be 5. B squared is 25. Let's get some axes here. Our center's at 0, 0 because we're not shifted. We're going to start off kind of like you would for the ellipse. That 3 is representing a horizontal distance from the center, which is at 0, 0. So I'm going to go 3 in either direction from the center, our horizontal distance or our a value, and plot points. Our b value is telling us a vertical distance from the center. So I'm going to go 5 up and 5 down and plot points. Wait a second. It feels like we're almost graphing an ellipse, but we're not. What we're doing is we're trying to create what's known as a central rectangle for a hyperbola, and this will really help us find the asymptotes. So notice, first of all, that the x squareds are coming first. I know it's going to be a horizontal or an x-intercept type of parabola. Let me graph in this central rectangle. This is not part of the graph yet. We have not graphed any of the hyperbola, but I want you to see why we're taking A and B and graphing the central rectangle. I can now see where the asymptotes are. The asymptotes go through the center and through the corners of that central rectangle. Can you see now why the equations of the asymptotes are b over ax and negative b over ax? If not, that's okay, we'll look at it. Let's see. We can see that this distance here was a, and this distance here was b. So the equation of each of those blue oblique lines is y equals a over bx. Our slope is now rise over run. I'm sorry, b over ax. I did that wrong. Rise over run. And the slope for that second asymptote is negative b over a. So our equations are b over ax and negative b over ax for the asymptotes. Now a, in this case, because it has x-intercepts, is the distance from the center of the hyperbola to the vertices. So our vertex is going to be here, and when I sketch in my hyperbola, I want to make it hug the asymptotes as best I can. Vertex, out, and out. So we stated the asymptotes. Let me actually write the equations. B over A is going to be 5/3. So y equals plus or minus 5/3 x. Those are the two asymptotes. I wrote two equations with kind of just a single term there, I guess, because of the plus or minus. But that is really two equations. I knew that it opened left and right and not up and down because the x squareds came first. And all we have to do now is find the foci. But don't forget that a squared plus b squared equals c squared. So in this case, a squared plus b squared is 9 plus 25, which is c squared. So c squared equals, what is that, 34? So c is the square root of 34. Now remember from our previous page that c is the distance from the center to the focus, not from the vertex to the focus, from the center to the focus. So if I go out root 34 and negative root 34 in the other direction, I can kind of see where my foci are. Now what is approximately root 34? I know it's between 5 and 6, a little bit closer to 6, so it makes sense where I plotted it. It's definitely beyond the vertices. What are the coordinates of the foci? Well, our center was at 0, 0, so if I go right root 34, I'm at root 34, comma 0. And if I go left root 34, I'm at negative root 34, comma 0. So there we have it. We found C, given our A and B. We sketched the graph by sketching in that central rectangle, sketching in the asymptotes, which had to go through the center and the corners. We wrote the equation of the asymptotes. We found the coordinates of our foci. We plotted the vertices. There you go. You can kind of imagine if B was shorter here, if B was shorter, what might happen to the asymptotes? I think they'd be a little bit flattened out, and our hyperbola wouldn't be as wide. Something to think about. Let's do one more example of graphing, and notice that this is not in the form that we want. I'd really like y squared over b squared and x squared over a squared. It is kind of our lucky day, though, because I don't really have to complete the square here. I gave you one where we already had the squares completed, but I think you'd know what to do if we didn't have something where the squares were already completed. Notice in our form, the right-hand side was always equal to 1, and in this case, it's equal to 36. What could we divide both sides by to make 36 into a 1? That's right, we can divide everything through by 36. So our first step here is really putting it into the form that we want. Now let's reduce. I see 9/36, that's the same as 1/4. And 4/36, that's the same as 1/9. So I'm just going to rewrite our equation so it looks a little friendlier. Y minus 1 squared over 4 minus x plus 3 squared over 9 equals 1. Notice a couple of things. This is shifted, but we know how to deal with shifts. We've seen them before. Instead of our center being at 0, 0, our center is now at -3, 1. If I look for those numbers near the x and the y, it's telling me to shift. Our a value, I always kind of leave a under x, but I know the number under the x is telling us the horizontal value here is 3, and our b value is 2, because a squared was 9 and b squared was 4. Let me sketch a picture so far. Oh, the other thing I know is because the y's come first, it opens up and down. It's going to have y-intercepts before the shift. Let me plot the center at -3, 1. Here's the center. And let's see, I'm going to create the same central rectangle, except now instead of starting at the origin, I'm going to start at the center. So I'm going to go 3 units to the left and to the right. 1, 2, 3. And I'm going to go 2 units up and 2 units down. All right. And remember, we're not graphing an ellipse here. We're graphing a hyperbola, so that's really telling me the central rectangle. And now I know the asymptotes are going to go through the center and the corners of the central rectangle. We haven't graphed any part of the hyperbola yet. This is all just a framework to get a really nice picture. And now because the y's came first, it was y squared minus x squared, I know that it's going to open up and down, and I can already see the vertices. They actually lie on the central rectangle. So here's the top arm, and here's the bottom arm of our hyperbola. Let me state the asymptotes. Now it's a little tricky because the asymptotes used to be plus or minus 2/3 x, but we shifted. Now here's the good news. The asymptotes are shifted in the same way that the hyperbola was shifted. So the asymptotes before the shift, if our center was at 0, 0, where y equals plus or minus b over a x. But we didn't want that. We wanted after the shift, because this is a shifted hyperbola here. So it's shifted 3 units to the left and 1 unit up. I can just take the same equation and create that shift on our asymptotes. 1 unit up, and 3 units left. There we go. So I'm not interested in my before shift asymptotes. I just kind of wrote that to help us see it. But our asymptotes are y minus 1 equals 2/3 times x plus 3, and y minus 1 equals -2/3 times x plus 3. They're shifted the same way that the hyperbola was shifted. Let's find our c value so we can find the foci. I know that a squared plus b squared equals c squared. So c is equal to the square root of 13. Now remember, c is the distance from the center to the focus. So not from the vertex to the focus, from the center to the focus. So the foci are at, let's see, had the x-coordinate -3, and then we were at 1, and I went root 13 above it, and -3, 1 minus root 13. So I'm just taking our center and adding or subtracting our c value to the y-coordinate because it opens up or down. So these hyperbolas kind of have a lot going on with them. We have to find the foci. It's sometimes at a weird point. We have to pay attention to if it's opening up and down or right and left. We have to be careful about the asymptotes, and a shift kind of sometimes screws that up. But I always recommend sketching a picture when you're trying to write the coordinates of the foci. And if we just get all of our kind of facts straight, where the foci are, where the vertices are, what A and B represent, how we sketch it, then it's really not so bad. Good luck!